pleasure to be here. What I'm going to talk about today is our last few years of experience in experimentation with a system not very well known for doing the things that I'll be talking about. In a gas discharge cell of helium-4 at room temperature, I'll be talking about effects such as slow light and negative group velocity light using a process that, thanks to Professor Deepak Kumar, I don't have to talk much about. The process is called electromagnetically induced transparency, or EIT in short. How does that happen? And all of that is what we are going to talk about. So essentially what I'm going to talk about is coherent manipulation of optical properties of material in gas phase. So what is this process of electromagnetically induced transparency, and how do you create slow or fast light? And then there are some storage and retrieval issues which I've decided now I'll skip completely. And then graduate ourselves from 3 level to 4 level, a tripod or a double lambda system, and the interacting dark resonances that Deepak was talking about. How do you go about that? And essentially this would be geared towards our work, so it's highly biased, our work both theoretical and experimental with room temperature helium-4. So just to begin at the beginning, when I talk about manipulating atoms by light, there could be 2 kinds of effects in such atom-photon interactions, and these, funnily, you can see even when quantized fields are in the vacuum state. So completely dark state, this is still a possibility. So one kind of effect are called dissipative or absorptive effects. They are described by the imaginary part of the susceptibility chi. So this corresponds normally to a broadening of the atomic energy level. For example, the fact that excited states have a natural line width, the rate at which a photon is spontaneously emitted from such states. So you can explain that by this imaginary part of the susceptibility. And the second type of interaction that we can talk about effects are reactive or dispersive effects. They are described by the real part of the susceptibility chi. These correspond to a shift of the atomic energy levels, not just the width. So there is a shift of the atomic energy levels. That is, atomic energy levels are also shifted as a result of virtual emissions and reabsorption of photons. This is a famous, for example, radiative correction for the lamp shift is an example of that. So the point is that when I couple atoms to fields, even if the field is dark, we are supposed to see these kind of effects in manipulation. So what is EIT? We are not the first, of course, to talk about it. This has a history, started way back in 1988-89, simultaneously by these 2 very famous groups, by Stephen Harris and Kocharovskaya et al. In Russia, independent of each other. And this, as the name suggests, refers to transparency or transmission of resonant light through an otherwise opaque medium. A medium that was initially opaque, it was not letting light go through. Somehow we managed to induce transmission in them. Now this is a quantum interference effect induced by a control field, and that also leads to something called a slow light that I'll explain. So I mean, I started my research career actually using interference, 2-photon interference in particular, with Professor Mandel in Rochester. And this is a different kind of a quantum interference effect that we'll be talking about. But as in all interference effects, when you be the undergraduate double slit, there has to be a coherence time that is involved, some kind of a limitation that we'll be talking about. So what is this EIT pictorially? The general scheme will always have this that Professor Deepak Kumar has already shown, but this is just for the sake of explaining my notation. The probe field, that is, I'm passing through the material. Material is a weak one, and that is coupling the transition from the level, say, B to the excited level A. And in the presence of a strong coupling, I'm going to alter the effect. So the general condition that we are used for EIT is that of 2-photon resonance. That's when this Raman detuning little delta is 0. So that this transition, the 2-photon transition, is exactly on resonance. And there's some problem with the notation, but not too much. The optical pumping, that is preparation of the material so that the ground state B is completely filled and there is nothing left at the level C, that is, of course, less efficient when the optical detuning here, denoted by capital delta, is non-zero. but it's still possible to have EIT when there is a finite capital delta. Let's just try to understand what this is. In a typical two-level system, two-level that you have selected by your laser, say that's shown by this red line in here. So say this is the two levels of interest for us, separated by an energy h bar omega naught, and I'm shining a laser of frequency red, shown in red as omega. Then the typical absorption and dispersion profiles look like this. Absorption is peaked when this detuning delta is 0. So the absorption has this kind of profile, and correspondingly your dispersion, that's the real part of the susceptibility, has this kind of a profile. Now what happens when we add a third level and a control field on the third level? So in the presence of this electromagnetic field, the profiles get modified drastically as shown in here. The old ones you can see in dotted lines in here, like shown in here, and in the presence of this control, we have got where I had maximum absorption, now I have maximum transmission, and likewise the dispersion profile has also got modified. Now this little window of frequency will refer to as the transparency window, and so this is possible in the presence of this control field, and when the control field is turned off, it back to square one where we started with, so nothing is destroyed. Now because of this extreme positive dispersion in this window, it's possible to have what we call slow light. Slow light, what it means is that the group velocity could be much smaller than free space speed, this denoted by c. So normally we are familiar with that. Refractive index of glass is say 1.5, refractive index of water is 1.3 or something like that. And semiconductors, you can have refractive indices of 3 to 6 or whatever. But here we are talking about large order of magnitude of an effective refractive index, which could be 10 to the power 5 to 10 to the power 6 to 10 to the power 7 and maybe 10 to the power 8. And its process of slowing down in a material, slowing down of light, is quite dramatic. And that is easily understood if you remember what is the expression for this group velocity, and it has this slope of this real part of chi, the curve that is shown in here. So in place of very steep positive dispersion, you will have very slow light moving through the material. So that's the idea. How do you explain this? As I said, this is a quantum interference effect, and the interference here is amongst multiple routes of excitation. How can a probe get absorbed? This is what I'm shining on the material, and it can get absorbed, and that's why you say that the material is absorbing on resonance, because the photon can pump this population from the state B to the excited state A. But this can also happen, so that's the direct route B to A, but it can also happen by an indirect route, that is of second order, that it goes from B to A and then A to C and back to C to A. Now these two processes, these two paths interfere quantum mechanically, and this is what we see, that these two cancel each other, and therefore there is no probe absorption along this path when this Rabi frequency is much weaker than the control field Rabi frequency. So in presence of a strong, not so strong actually in real terms, of a coupling, it's possible that this probe will actually go through the material. So that's the meaning of EIT. Initially it was opaque. Now it has become transparent because I have induced transparency by this control laser. Now this is really because of this very delicate and fragile concept that I talked about, quantum interference between two possible paths of excitation that actually happens. Now, as you know in interferences, the coherence time that I was referring to in this case is really this coherence time that is that goes by the name of Raman coherence time between these two lower levels B and C. So as long as this coherence is established, this effect is possible. So this is a very important parameter in any experiment or any theory you want to do. How long does it take to destroy the coherence between the two lower states once you have established it by your coupling field? So we'll keep that in mind. So the idea is that it's very simple, that if you have a three-level system as shown in here, and the two fields, you can treat them classically if you wish, and then you write down your interaction Hamiltonian as shown by Professor Deepak Kumar, and you can solve this problem to get the new eigenstates of the problem. And what has been described in great detail in the previous talk, the dark state is shown in red in here. This state A0, the new state that you create, an eigenstate of the atom plus field combination, has no component of the upstairs level A. Therefore, this is the dark state. Light is shining on it, it doesn't see it. So that's the meaning of darkness, the state in the atom which doesn't talk to the light field at all, though it's the other two states are components of A. So on two-photon resonance, there's zero probability of getting excited. This dark state has zero probability of getting excited, because as you can see that the dipole moment between these two states, A0 and upper state, is actually 0. So there is a phenomenon that everybody studied earlier. When the two fields are of equal magnitude on the two arms, we produce what is called coherent population transfer from initial state C to B, and when you start with two populations that are restricted to the ground state, and you eliminate the effect of spontaneous decay from state A by the use of this. And so these two states are called coupled and non-coupled states. EIT is a much more subtle effect that we are talking about. In EIT, what happens is one of the probe field is actually very weak. So you look at the dress states created by the coupling, and then how does the probe react to that. So the dark state in this case happens to be the ground state of probe absorption. So the population is all transferred in here, but when I shine in, nothing gets transferred up there. So that's the funny part. Nothing gets transferred up there because the probability of transfer here gets cancelled with probability of transfer through the coupling field. Now this is really the effect, and if it is such a fragile quantum mechanical effect, can we really see this in a bulk system? And that also a challenge thing to do it at room temperature. No cold atom, a very simple and very inexpensive setup. This was done in collaboration with a group in Orsay. My good friend Fabian Bretneka for very long years. And in this project, the collaborators are Thomas Alaprete, he's a PhD student, and Fabian Goldfarb, who really set up the helium experiment in Orsay. So the work started actually quite some time back with a PhD student of mine who graduated early 2009. And what about helium-4? Helium-4, of course, has been used a lot for cold atom systems. Here, remember, we are just using a glass discharge cell. It's called a metastable helium-4 because this state, 23S1, has a lifetime of 8,000 seconds. It's almost like stable. So that's why the name metastable state. We are not using the true ground state, which is hiding a bit here, 11S0. We are not using that. Using a discharge and giving it energy of about 20 electron volt, you pump everything to the metastable state and it stays forever. The transition we are probing is really is at 1.083 micron, and that is the transition from 23S1 to 23P. Now, how do you actually create a lambda system out of it is what I'm going to talk about. The attractiveness of this system is that it's a very, very simple level scheme because nuclear spin is 0, unlike rubidium. And the way we actually did the creation of a lambda system, almost creating by design, is using polarization selection. So the way it's done is that there is no magnetic field applied in the first set of experiments that I'm going to describe. And what we do is, so the ground levels are all degenerate, and we apply the control as a circularly sigma plus polarized light, and the probe, what you are going to send through, as a sigma minus negative left circularly polarized light. And after a few cycles of absorption and then spontaneous emission, the level scheme that you're left with is essentially a clean free level, because that's this transition is allowed by sigma plus, this transition is only by sigma minus, and spontaneous emission creates this, and this is how you actually end up creating a very good clean lambda system. We are, of course, not the first ones to come up with this. This was done in a different context, first by the group of Alan Aspect in 1988 and so on and so forth. And of course, this is our paper, the second one that is cited in there. So this is how you create a lambda system, and in this particular experiment, we used this 2,3p1 level. Now, the time here that is shown, 8,000 seconds, is not really the relevant time for an experimentalist. And I'm going to come back to this point. So it can be very, very long-lived, but if the atom is transiting, I'm not freezing the atom. This is not a cold atom system. So the atoms are actually moving through the laser beam. So as long as they stay in the laser beam, that's your interaction time. The moment it has transited out of the laser beam, the work is over. So this is much shorter, of course, than the metastable lifetime that is shown in here. So you have to keep that in mind. So this became our favorite system for a number of reasons, and I'm going to talk about that. When we first started work with room temperature helium, people told us that this is actually not possible. But it became possible. First, we were attracted by the fact that the transition I'm talking about has a very, very strong dipole moment. And therefore, you can actually buy off-the-shelf lasers and very low-power lasers. And the saturation intensity shown is watt per meter square. So it's essentially a milliwatt laser that would do the work for you. Then two remarkable properties of helium, metastable helium, that even if they're colliding, because you can't avoid that in a room temperature gas, there is no problem of depolarizing because of collisions. And this is again well known, and we just utilize this. The first property I'm talking about is known from 1980 onwards, that collisions with ground state helium do not depolarize metastable helium. Second property I'm talking about is once the metastable atoms are spin polarized, penning collisions between themselves are nearly forbidden. That doesn't happen. The details of it is not the subject of discussion today, so I give you the references if you're interested to figure it out. So we essentially used these two remarkable property of collisions in helium-4 and then added our own understanding of what is going on, and that's what I'm going to spend 1 minute on. As I pointed out, the fact that metastable helium has 8,000 seconds of lifetime doesn't really matter. What matters is the transit time. How long is the atom going to stay in your laser beam? Now, it turns out people always thought that collisions are going to kill the very fragile quantum effect we are talking about. In collisions, the devil's advocate actually came into our rescue. Collision is a good thing in our system, and I'll explain why. There are 3 points, 2 are written here, one more I'll talk about in a minute. What diffusive motion does is that if you didn't have, some hidden slides I guess, if you did not have collisions, then the motion of the atom through the laser beam would be just ballistic. It would just fly through. Because of collisions, it's getting scattered around, and the motion of the atom is not ballistic, it is diffusive. And as a result, the transit time through the laser beam increases. As a result, the Raman coherence time increases. So collisions are actually good if they do not depolarize the helium atoms. Second, what we find is that we have velocity changing collisions. Here is a room temperature system which has a Doppler profile of say 1 gigahertz. It's a huge bandwidth, and here you're pumping with a laser which has kilohertz, hundreds of kilohertz of line width. So essentially you would not be able to pump all of them because they will not be on resonance. It's a Maxwell profile, Maxwell-Boltzmann profile or Doppler broadened system of 1 gigahertz, and you're pumping with a kilohertz laser which is going to cut a hole in a very small region. What we show is that because of velocity changing collision, we are able to cover the entire Maxwell-Boltzmann profile. I'll come back to these 2 points shortly. When we had to do our theory ourselves, we found out all these points had to be considered. First, the experiments. The setup was really a tabletop one, very simple. What you have is a laser, diode laser in here, which is operating in single mode, and then through this polarizing beam splitter, you split the same laser beam into 2 components to create your pump and probe, both from the same laser. Okay, and this is just these AO1 and AO2s are acousto-optic modulators, which in the photograph are these 2 red pieces in here, and they allow you to tune in the frequency and also the intensity a bit, and then they're combined together with sigma plus and sigma minus polarization as pointed out through optics I would not get into the details of, and then they're collinearly propagating through your helium cell. the helium cell in this experiment was actually 2.5 centimeter long. It's really, really a small cell. The huge thing that you see here is because it was shielded with new metal box to avoid stray magnetic field. And that's why it's looking so huge. The cell is actually sitting inside in here. And then you detect the probe transmission through the cell by your required optics. So that's really the idea. And that's the very, very simple tabletop setup. A typical EIT resonance, as we call it, is looks like this. So remember that at Raman detuning for a two-level system, absorption should have been maximum. It should have been the other way around. Now we find that transmission is maximum at Raman detuning equal to 0. So the probe is on resonance, but it doesn't get absorbed, it gets transmitted through. And the width on resonance we have found less than 10 kilohertz. This typical one that is shown is about 11 or 12 kilohertz in width. So this is quite remarkable, a property that we could show. Now this was published in 2008 in EPL. As I pointed out, the moment you have a modification of the transmission profile or absorption profile, you also have associated with it the real part of chi playing some role. So the dispersion profile also changes, and as a result it's possible to create a slow light. This slow light is reserved for cases where, for example, the typical data that is shown in here, you are getting effective refractive index of the order of 10 to the power 5 without having done anything. The cell is really, really small. It's only 2.5 centimeter long. If you had a longer cell, of course, you would slow it down further. So this was quite interesting to see that depending on these two sets are for two different beam profiles, meaning diameter of the beams, that modulates the transit time through the atom, of the atoms. So this is something that we could see, and when we tried to fit it with existing theory that fits with the other parameters of EIT, we found the fit was no good at all. And so there is some qualitative matching maybe in the wings of it, but as a function of the coupling beam intensity, which is also not much, you do not quite have a fit of this. So essentially it told us that we had to do our own model to take into account room temperature gases where collisions are unavoidable. So collisions that people actually thought were a bad thing, we felt that we need to actually take them into account to model what we are seeing. So the effective model is as pointed out earlier, you have a three-level atomic system with two classical fields. And then we have taken into account collisions and other relaxation processes in this model, which is shown by this relaxation matrix R in here symbolically. Typical rates that are of interest to, if anybody is interested in experiments, is something like that. The Raman coherence decay that we are talking about is of the order of 10 to the power 4 hertz or so. Now, this essentially means that all your manipulation that you want to do in this system has to be done by 10 minus 4 seconds, okay, which is not a small time. It would have been really, really smaller, orders of magnitude smaller, if the atom was actually going through zoop past the atomic beam. So this increase that we got, the order of millisecond rather than microsecond, is because of collisions in the beam. And the rest of the parameters are nothing to be fitted. They're all decided, pre-decided by your system. So we already knew what would be the decay lifetime of the upper state. We knew what would be typical collisional dephasing. This is a function of the pressure in the gas. How dense is your gas? And so all these things we knew, and approximate range of the decay due to velocity changing collisions was also known. So this is how we went about modeling this. And as I pointed out, and just to justify the time scale, is that if you have just no collisions at all, if this is the laser beam, the atom would be transiting through, because it's a room temperature gas, it's moving all the time through the width of the laser beam in no time. So because if you really do a small back of the envelope calculation, taking your metastable helium as a hard sphere, and mean-free path would turn out to be about 0.1 millimeter, given our temperature was 300 K and pressure was 1 torr. So if you take a 1D random walk, you actually get your transit time to be about half a millisecond, pretty much like what we have estimated it by other means too. So if the moral of the story with collisions at this point is that if collisions do not destroy coherences, they help to increase transit time and therefore the Raman coherence time, which is a very, very good thing. The second point that I have made is that if you have velocity changing collisions, this is what I was talking about, that you have a Doppler profile, that is you can think of the width of the upper level to be really broad. It's like 1 gigahertz broad. So the transition is possible within, let's say, 1 gigahertz, and your laser is actually trying to create little holes on this profile because it cannot span, at most it's megahertz, it's actually hundreds of kilohertz, it cannot span the entire profile. But if I have velocity changing collisions, and they're very, very rapid, then it's possible that we almost preserve the Maxwell-Boltzmann distribution and the optical pumping becomes almost velocity independent as if it's seeing the full profile. And this is possible only because you have very rapid velocity changing collisions which was happening in our system. The third interesting thing that we found out by accident actually while doing the modeling is that it's also possible because of collisions, the atoms are prepared in their probe ground state and they move out of the laser beam, then they are kicked back because of collision before decohering. So it's possible to have almost like pumped atom back into the system more than you had. So if you do a simple theory without taking into account of this sort of repumping of the atoms back into the laser beam, then you'll find your coherences are all going above 1. So what we had to do really account for this, of course, diffusions of atoms out of the laser interacting regions, and then they are returning before decohering. So pumped atoms come back to the laser beam as a very positive thing. And again, this is happening because of collisions. Collisions are sending them back, and they're still prepared. So this had to be taken into account in our model that we did through this parameter that we call beta. So this was, of course, a PRA in 2009. Very interesting case that we saw was that if you really do not have single photon, optical detuning is non-zero, then rather than having a resonance profile which is symmetric, more or less like the black one in here, it increasingly becomes asymmetric. Now, this was something, this is really a signature of two-photon process that we claim that we have here. Otherwise, it's possible to have saturation of an absorption and therefore transmission. This nonlinear effect of saturation of an absorption, that is, when you have lifted all the population upstairs, there is nothing to absorb anymore. So that also leads to transparency, but that's not the kind of effect we are talking about. This, without getting into the details, this is really a signature that this is indeed a two-photon process of the kind we talked about. So on the left are our experimental data, on the right are a very simple modeling using density matrix equations of the kind we talked about, and the fitting were almost all decided. Only two fitting parameters are shown in this circle in here. This was for velocity changing collisions, and this was for the unequal transition back into the atom of prepared atoms. Okay? So having done this, we matched what is the resonance width, the EIT width, as a function of the coupling beam intensity, and the dotted points here are the experimental region, and you could of course extend it for various change of parameter. Of interest here is this Raman coherence rate, which is given by inverse of gamma r. If gamma r is increasing, that means Raman coherence time is decreasing. The width shifts like that. The fact that we get this linear variation with coupling beam is, we are the first ones, without having to use any approximation, to show that this is actually possible with nothing else fitted. These are all predetermined parameters. From these results, we extracted our velocity collision, changing collision parameter alpha, and from the next set of data, we extracted the beta parameter, and with the same values, we fitted these millions of data sets that we had. Here is a typical result on delays, group delay. The delay as a function of the coupling beam, I have already shown you this. So this is a signature of the slow light, and the dots here are the experimental data. They are almost lying on top of our experimental fit. So this is not cooked up. This is actually very, very sincere fitting, and we could even predict what would happen, for example, if T naught, this is the initial transmission, which depends on the density of the atom. How dense can you get? Is it possible then, the question is it possible to stop light inside your cell completely? Slow it down so much that it stops inside the cell and comes out only when you turn off the control field. Is it possible? Well, the answer for this system is, of course, no. And detailed results of all of this had been given in a review article that was there. We had some fun talking about various things about the dark state, bright state basis people talk about, but I will not get into the details of that. This is supposed to be an equivalent sign. This work that I want to talk about now is a natural extension from what we have done with three-level systems. Is the work done by Santosh Kumar, PhD student in JNU, again in collaboration with the group in Orsay. Santosh is sitting in the audience. So we got ambitious and thought that, okay, in the same system, if you could carve out a lambda system, why don't we start the game kind of in the same spirit that Deepak was talking about, that we have got one dark state. Now, can we actually play with the various dark states and see what is the effect? So there are two distinct possibilities one can see, is that depending on which level, which transition you are sharing, are you sharing the probe or are you sharing the coupling? There are two interesting systems that one can talk about, and this is what we got into next, is to play with four-level tripod. The name suggests the geometry of it looks like a tripod or a double lambda, and you have essentially double EIT kind of configurations, and what do you get out of that? When you have to think of this, of course, you have now, instead of a three-level atomic system, you have a four-level atomic system, and instead of two fields, you have now three classical fields, and they have their own detunings. So all we are planning to solve is density matrix elements in the steady state regime with all relevant relaxation processes. So this is, of course, much more complicated than the three-level lambda, and hence, of course, much more interesting, provided you can play with this. We use the same system that we knew, but a slightly different transition. It's the same metastable helium system. We use discharge to come to the metastable 2,3S1 state, and use the same diode laser system to couple to 2,3P, but the sublevel we are now choosing is a slightly different one. Previously we had talked about 2,3P1, now we are interested in coupling to 2,3P0. This is separated by about 30 gigahertz from the next sublevel. Therefore, this is totally isolated a transition. There is no way of mixing up. When you want to pump to this, there is no way you can mix up with this pumping in here. So in a complicated atomic system, it's possible to isolate each and every transition very, very selectively, and that's the advantage in here. So in the first simple experiment, what we did is really use, through again polarization selection, where the probe that we are talking about is sigma, and it's shown in here, and C for control or coupling is actually a pi transition in the helium cell. So a small magnetic field has been used perpendicular to the direction of propagation by a homemade Helmholtz coil, and this allows us to remove the degeneracy of the lower states as shown in here by a Zeeman splitting, that is delta Z. And the transition we are talking about is for both probes, the sigma can be split into sigma plus and sigma minus. We are not doing anything. The atom is selecting by itself. That sigma plus would take atoms from this state to the upper state, and sigma minus will take from this sublevel to the upper state. And the control is turned on the 0 to 0 transition, that's the pi transition. So when we use this first simple experiment, what you find is that, well, there is nothing really extraordinary about this. We have two EIT systems independently, and the sum total of that is what we see. This is on the left-hand side are our experimental data, right-hand side our theory, they match fairly well, and what we are getting is by a fit by incoherent addition. Two separate EIT systems, they just add on and we get the result. The different curves in here are for different values of the magnetic field. For example, the central peak here corresponding to a very low coupling power, as you would see, even the control is of the milliwatt range. It's not really very, very high. So milliwatt, microwatt range is what we are talking about. For a very small coupling power with no magnetic field, that is no splitting of the Zeeman levels, there is a peak that is the typical EIT peak. the transmission at Raman detuning 0, Raman resonance. And the moment you turn on magnetic field higher and higher, you see that where you had a central transmission peak, now you have a flat line and two separate peaks at plus minus delta Z, the Zeeman detuned peaks appear. And this effect continues, and it's really like having two EIT systems, they are adding together and giving you this result. Second was a funny experiment. We now interchange the roles. Remember, previously we had the coupling at the center. Now we put the probe at the center, the two couplings at the two sides. If you do that, then so essentially your coupling control fields are sigma polarized and the probe field is pi polarized. If you choose this, then you suddenly find that the situation has changed remarkably. And you have some kind of an interference between the two dark resonances because of the two EIT systems. What are we seeing? The black curve is the same as before, is B equal to 0. And then when you turn on the magnetic field, and here we are going up in coupling power, this side is experiment, that side is theory, that you find there is a switching centrally where you had a black peak, that is transmission was high, suddenly you have a red dip. From black to red, there is a switching from transmission to absorption, and this is a function of the magnetic field. So this is field controlled dynamic switching of a material. What does that mean? I'm shining light, it was coming out all right, suddenly I turn on the magnetic field, it got blocked. It's almost like a switch that you would have on-off switch, and that is exactly what we have been able to create in this. A very sharp absorption dip at the line center. And using our theory, using all the decoherence processes, we actually managed to fit it fairly well with parameters that were not fudged at all. These are all fixed by your experimental system. Now, to give a very simple picture in terms of dress states is difficult in this case, but we have an understanding of what is going on in this case. So the next problem was really to go ahead and probe in between cases and finding out what kind of interference is possible in this. Now, the results that I just talked about, which was published earlier this year in PhysDev A, and then we have loads of data that we need to figure out what to do about, and that's what we are fighting for the last few months. Understanding the system very qualitatively, till then you do not want to publish, it's not so easy, and we are going to do this fairly soon, it's almost ready. But in between we had fun. As I said that I played with the basis, change of basis, the nomenclature people use dark state, bright state, to the states that we are talking about in this configuration were already interesting for us. But now we also realize that there are lots of work going on in the application side of such highly dispersive materials. If you put such a highly dispersive material in a cavity and then therefore make out of it, for example, a gyroscope, can you affect the sensitivity of the gyroscope? There are a whole lot of literature available in the last couple of years on this. And something very simple that you can say, again, sorry about this, this is supposed to be an equivalent sign. This expression I have already shown, this is an approximate one, this is supposed to be an approximate sign, is that if I am defining my group velocity as C by ng, this being the group index, and this of course depends on the slope of this curve, real chi, as a function of frequency. Now, I talked about slow light, which is the case when this ng is much larger than 1. I showed experimental data when ng could be as high as 10 to the power 5 in a small cell. We have gone up to 10 to the power 6 without any problem. So this makes the group velocity of light through the material extremely small. It's like a cycle going through the material. Now, what about the other case where this is not a positive dispersion, but the slope is the other way around? If the slope is the other way around, then we call that light fast light because ng becomes less than 1. So it seems a little odd that then it's possible to have either your group velocity greater than c. This would be the case when ng lies between 0 and 1, or it's possible to have your group velocity negative. Your negative group velocity would mean ng is negative. Now both these cases are termed fast. Okay. Now fast light, if you think of it, is it violating Einstein's causality? No, it's not. It's counterintuitive but does not violate causality, because now we know that information propagation is not described by this Vg, but is better described by the discontinuous front velocities of the signal. So, in order for it to carry any information, there has to be kinks in the front of the signal propagation. So, this is the situation today, and we started looking at our data to see if we could actually have negative group velocity in our system, and this was published by invitation in the French Academy. We looked at our data and we saw that indeed in the delay curves, if you for example concentrate on this curve C that we presented in this paper, the corresponding dispersion is like this, and it's really negative dispersion. So, this indeed allows us to take our group velocity from a plus value, plus 10 to the power 4, to a minus 10 to the power 4 by change of optical detuning, capital delta. So, this is something that we have already seen, and correspondingly this is the regime of fast light. So, the question we got interested in terms of applications, and this is something that we probed in this optics letters earlier this year, photon lifetime. There is no photon here, this is really cavity field lifetime. And the idea was the following, that people were claiming, a group of people from Chicago, that it's possible to improve the sensitivity of gyroscopes by putting a highly dispersive material inside, which shows highly dispersive material. By that I mean the group index is above 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6, and so on and so forth. And then we showed that they were talking about if you put in such a light inside a cavity like that and turn off the field, the decay of the field, they said essentially, because it's a monochromatic field, is going to be governed by its phase velocity. Now, the moment some field, to cut a long story short, is that the moment something is decaying in time, it no longer stays monochromatic. So, that's the simple wisdom which we demonstrated in this paper, and I invite you to go through this. Having done this, now we have gone ahead, and this is a paper we have recently submitted to Nature Photonics, that it is possible, what happens when instead of slow light, you have fast light, and we could create negative group delay. So, suppose in a cavity, we put a material which has a very positive, very high positive dispersion, and what happens to the constant of decay rate? Because as everybody knows that this is really a very funny situation, counterintuitive, very much counterintuitive, for the simple reason that when you turn off, what does fast light mean? It would, negative group velocity would mean that before the pulse enters, it comes out from the other side of the material, and somehow this people and the intensity is actually going to increase with time. You can't really apply your regular concepts in that, and we showed that the transmission profile gets completely modified by such a dispersive material inside the cavity. Instead of a single peak Lorentzian, you have multi-peaks essentially, and as a result, the decay cannot be described as an exponential decay. It's not, and two such examples we have worked out very, very well. Essentially, it means that for fast light, there is no concept called a lifetime. If you have an exponential decay, you can talk about what is the lifetime. If you have multi-peak structure and as a result, a very complicated decay in general, which is demanded by theory, then you cannot really possibly talk about lifetime. So, the message from all these studies of ours, very carefully done, is that one needs to be very careful with claims of potential applications that are coming from many groups all over the world. I forgot to mention very interesting contribution from Sylvain Swords, who works at Thales in France. These two pieces of work was done in collaboration with him. So, the other kind of work that we are interested in that I am not going to talk about, it was there already in my scheme, but maybe I will cut the talk a little short, is about what Professor Deepak Kumar talked about, is as everybody knows that photonic qubits are appropriate for quantum communication over long distance, but they are difficult to store as memory, whereas atomic qubits are good quantum memories, but difficult to transport over distances. And what he talked about already, and I don't need to talk about this at all, is really how to have an atom-photon network where you transfer a piece of information from the photon system to the atom, and from the atom system back to the photon without knowing what that information is. Because the moment you do a measurement, that information is lost anyway. So without destroying the quantum coherence processes, is this possible to do? So there are many issues involved in this transfer problem that Professor Deepak Kumar talked about. And the one that he didn't show, I'll show you here, is this work that we did together some years back, but just got published this year, on analysis of this adiabatic transfer process, how fast is fast and what is really adiabatic in this. So I really want to cut this talk short. So let me just summarize what we have said. I hope I have been able to convince you that 3-level atomic systems are extremely versatile. We have come a long way from the old 2-level systems where we played with resonance and so on and so forth. Addition of one more level and a control along with that makes life really, really versatile. We have explored a nonlinear method, a very nonlinear method of coherent preparation that produces remarkable changes in the optical properties of a gas phase medium. I talked about the example of helium, but this is known for other systems as well. And this is all because of laser-induced coherence, the controlled laser-induced coherence of atomic states that leads to quantum interference between excitation pathways, and this is responsible for the control of the bulk optical response. The one I'm talking about is really electromagnetically induced transparency, as the name suggests, is induced by the control field, transparency that is induced by it, and application of that would mean that it leads to switching that is dynamical. From absorption at resonance, you can create complete transmission and back to absorption and so on and so forth. So it really works as a very fast and dynamically controlled switching device. And the example that we have given is about EIT in metastable helium-4. It's a very good system, has its limitations, but it has not been probed fully well. As a result of this transmission profile modulation, it's possible to create either slow light or fast light. The fast light regime is not well probed, but it's possible to do that in the system by variation of the single photon detuning, very simply, as we have already demonstrated. So the attraction of this very novel system is well known in the cold atom community, not so well known for room temperature system, is that if I use it room temperature, of course, it's very inexpensive and it's very easy to use. There are very strong dipole transitions, low saturation intensity, so I can use very low power, microwatt, milliwatt power of lasers off the shelf and work in the 1 micron regime. Because of non-depolarizing collision between identical helium atoms and because of spin conservation, all this is possible at room temperature with a Doppler width about 1 gigahertz. So we could design a clean lambda system, a 3-level lambda system that is thanks to just polarization selection. And the group, we have observed group velocities of a few thousand meters per second. From 10 to 8 meters per second, we could come down to a few thousand meters per second, but this was controllable as a function of the power of the control laser. So this is in a small cell of only 2.5 centimeter length, and that was done at room temperature. If you have now done experiments with much longer cells, as I forgot to mention that, it is possible, of course, to slow it down further. From the 3-level system, we have graduated ourselves to a 4-level tripod system using the same system of room temperature helium. And in this case, we use a very weak magnetic field, and again, polarization selective transition. We have seen interesting interplay between double dot resonances, and the application many. We have not gone into the pulsed regime. All these experiments I reported are done in CW, continuous wave regime, but we could think of an extension in the pulse regime and therefore actually apply this to coupling induced switch, magneto-optic switch, and so on and so forth. So you control this either by the coupling laser or you control this by the magnetic field. The switch I'm talking about is transmission absorption, and so on and so forth. And of course, it's helpful to have a modeling of the system so that you can predict before you do the experiments, and our numerical simulation of the atomic density matrix equations explains the broad features of the system. We are now struggling to get some physical understanding in much more complicated systems. There are many applications that I have mentioned, but there's some immediate perspectives that rather than completely stopping lights, it's possible to use this as a delay line that people are interested in. Again, there are some industries that are interested who do signal processing at 1 micron. That's our laser level. And if I want to increase the EIT bandwidth, that is the EIT window, then I need much high power lasers. That itself is a technological challenge. How high, I am not giving you the numbers yet. To get higher delays, I said slow down by 10 to the power 5. Suppose I want to really slow down and stop. What it means is higher optical density. That would mean that I need to actually increase the pressure inside, and that would, or increase the effective length of the cell by multiple reflection. Now, increasing the density, of course, would bring in some bad effects of collisions. So there is a trade-off right here. So there is a lot of work going on in trying to figure out what is the optimal thing for this. It's possible to use these helium cells in the negative group velocity regime that I talked about with a particular range of single photon detouring. And Thales people, again, the reason they are involved is that they're interested in passive cavities for rotation sensing for applications they are interested in. So I think I stop here and take your questions, and thank you very much for your attention.
So now we have time for questions.
It's a difficult but very nice area. Can you give us some insight into why sometimes the group velocity and sometimes the discontinuous front velocities correspond to information transfer velocity?
Yeah, it's actually kind of difficult to draw a picture and explain this. I'll tell you how it has evolved. We started pushing the front, and then earlier what could pass off as group velocity, not the phase velocity, but the group velocity being less than c. Now that you have violated that, you need to look into it and see what the simplest answer is. That if you plug this in, this is all following from Maxwell equations. There is nothing being violated anywhere. So people have started looking into, this is an old paper, which I think you know, Sommerfeld and Brillouin both have worked in these areas, and they did these things as an abstract mathematical exercise to see whether what exactly is the limit, because nobody has proven Einstein's causality relation from fundamental principles today. So this question has raised a lot of problems already, but there is nothing in this having a dispersion curve tilted this way or that way that violates Maxwell equations. So this is nothing against any fundamental principle. So you need to understand how do you code an information? The information has to be coded. It cannot be a smooth signal, because then there is no information. So information essentially is coded into something on a smooth carrier. So the information content of it has to be because of a discontinuity somewhere. So even if the group velocity is exceeding c, it doesn't mean information is getting transmitted at more than c, because the front never exceeds c. So this is really the wisdom of the last few years. Relooking at things, I think people knew already. I mean knew meaning had worked out already. So it's not possible for me to give you a pictorial representation, as you know, because the moment you start drawing a pulse through such a material, it's an absurd picture. That essentially means the moment before the pulse enters, the outgoing pulse comes out, and the second pulse starts traversing reverse. That's really the picture. But this picture essentially would mean the intensity of light starts growing with time, which is an absurd picture. Because this picture fails, and that's what I think our idea is, that this picture of a pulse entering and then coming out does not work in this funny regime. But the mathematical part has nothing against Maxwell equations. It's actually all derived from there. That's the best explanation I can give right now.